to the given slide. Okay. So what we are looking for is this slide. This is actually the tutorial based on the frequency response. So just for your information, some of the detail, some of the formula will be referring to the yesterday notes. All right. Can you download the question, the tutorial?
Yes, doctor.
All right. So this question is taken from the previous final exam question. So let's take a look on the first question. Okay, in this first question, the figure 1 represents a block diagram of PD control of two tanks in series with transportation lag in the measuring element. The PD controller parameter are Kc equal to 10 and tau d equal to 0.5 minutes. The control valve has time constant of 2 minutes and unit gain. So what can be extract from this information is first we need to refer the block diagram. So you have the block diagram here where it's a little bit different compared to the standard because you can see the U here, the U represent the disturbance. So this U as your input and this you have the R and the C. So here we can interpret the C is your output variable. And the U here represent could be the disturbance input. However, there is no block diagram over there, just arrow. And then here you have the R. R is for your, normally this one is for the set point. So in this case, the question mentioned the PD control. The PD control. So that means the type that control for GC is PD, where the GC equal to Kc 1 plus tau ds. So if you remember, if you have the PID control, the common transfer function for GC is Kc in bracket 1 plus 1 tau is plus tau ds. So this is the PID. However, the question gives you the PD control. So that means no I, no integral term. So when you don't have any integral, that means the tau I is neglected. So based on the PID, when the tau I is neglected, this reduced to the Kc 1 plus tau ds. So this is what is meant by PD control, where the P stands for the proportional, the D derivative, no I in the transfer function. So this one, PD control of two tanks in series. The tank, however, is not given. So that means it just represented by block diagram. And then the next information, transportation lag in the measuring element. The transportation lags in this case referring to the time delay. The information for the measuring element. Measuring element in this case referring to the GM. So the GM in this case will be this exponent negative 0.1 s. That is what is mean by transportation lag. That means you have a lag during the process. Lag in this case referring to the delay, response delay. How long it has been delayed is 0.1. So the time delay for this part, exponent negative 0.1 s. And then they give you the information of the controller parameter for PD, which is the Kc equal to 10. and tau D 0.5. So we will just substitute inside the equation Kc equal to 10. 1 plus tau D is 0.5 S. So that complete the GC and the measuring element. Lastly, the control valve has time constant of 2 minutes and unit gain. So this referring to the control valve referring to the GV. So the GV is here, and then the information time constant of 2 and unit gain. That means it is in the first order. For the first order, you have KV tau V S plus 1. So this is the first order, where I put the KV. V means is referring to the gain of the valve. So for this part, it gives you the unit gain. So that means in this case, it's referring to 1 because you don't have any S on the unit, just unit. So it is a singular. So the KV itself will be equal to 1 over tau V is the time constant for valve is 2. So 1 over 2S plus 1. So this is the transfer function for control valve. So we have the GC, we have the GV, we have the GM. So the remaining itself, in this case, you have 1 over S plus 1 and then 0.1 S plus 1. So automatically this one should be your GP. So you have the GP given in the block diagram. The GC is based on the PD control, which is GC equal to 10 in bracket 1 plus 0.5 S. And your GV 1 over 2S plus 1, and the GM in this case exponent negative 0.1 S. So this is the information that has been extracted from the given sentences. Any question? So here we don't have the question yet. We just extract the information. So for this part, this is the list of the equations. The question for the given question where first A, determine the expression of amplitude ratio and the phase angle for the given system. Based on the expression, we need to plot the Bode diagram. And then from the plot, we need to find the gain cost over frequency WG and critical frequency WC from the Bode diagram. D, compute the phase margin and gain margin from the Bode plot. Comment your answer. And lastly, calculate the phase margin and gain margin without using Bode diagram. So in this case, we can see that question B, C, D, you need to use the Bode diagram. Bode diagram. That means the graph. But the E is different without using Bode diagram. How we can calculate the phase margin and gain margin. So meaning that in this case, we can compare. For example, question D, phase margin and gain margin from Bode. Question E, phase margin and gain margin without the Bode diagram. So that means there are two ways to calculate the phase margin and gain margin from frequency response. The first one using the plot, the second one just using the calculator. So we take a look one by one. We start from A. So based on the transfer function, we have the GP. So this is the GP given in our equation, the GM, the GC, and the GV. So for this part, normally in the frequency response, we just need to obtain the overall closed transfer function in the closed loop. So this means we just need to include the GP, the GV, GC, and the GM. Why we need to account for all of this transfer function? So we refer back to the plot diagram. So the block diagram here, we want to consider the closed loop behavior, closed loop stability. The closed loop itself is in this range. Whatever transfer function inside the loop. So for frequency response, whatever block diagram available in the loop need to be considered. And normally we just use one loop. We don't provide you two loops. It will be getting complicated. So what you need to do, you identify the loop, you count how many transfer function available. In this case, this is 1, this is 2, this is 3, and you have 4. So you have 4 transfer function available in that loop. So the next step is to multiply all of the transfer function. So here, that's why we multiply the GP, the GV, the GC, and the GM, because all of the transfer functions are available in the loop. So in this case, we have the GP multiplied by the GV, multiplied by the GC, multiplied by the GM. So we list all of the transfer function available and multiply it. So for this part, you can see from the slide, you have the 10 in bracket 1 plus 0.5s exponent negative 0.1s in the numerator. And on the denominator, the bottom part of your equation, you have the s plus 1, 0.1s plus 1, and 2s plus 1. So in this case, you don't need to expand. No need to expand the equation. What you can expand is just if you have a number, the exact value, for example, 10 multiplied by 2, 20. So that one you can multiply it. But in this case, we don't expand anymore. We just leave as it is because the next step involves the transformation of S Laplace into frequency term. So here you have the GOL equal to 10 in bracket 1 plus 0.5s exponent negative 0.1s. So you have this one is one term, this one is one second term, and this one is third term on the numerator. And the bottom part, you have this as term number 4, this is a term number 5, and this is term number 6. So you have 6 different terms for frequency response. So based on this, we list one by one. So here you can see in this table, I list all of the transfer function terms. So you have 10, 1 plus 0.5s, exponent negative 0.1s. So this one is on the numerator, on the top of your equation. And the bottom part, s plus 1, 0.1s plus 1, and 2s plus 1. This one is on the denominator. So in this case, we want to convert the transfer function into the amplitude ratio and the phase angle. So we go one by one. We start with the transfer function 10. So for the 10, when you convert into amplitude ratio, it produces also the same number. It does not change because the number when you try to Laplace it is still the same thing. And then for the phase angle, whatever the number you have, automatically it becomes 0. Because the number normally has a horizontal line. So when you have a horizontal line, it's a steady line, there is no angle. It just represents a straight line. So that's why your phase angle becomes 0. This is standard for any kind of value that you will use for transformation. And then we go for the second term, 1 plus 0.5s. So this, if you remember, if you have tau s plus 1, the amplitude ratio automatically square root tau square W square plus 1. So this is the standard transformation for frequency response. So that's why in this case, you can see square root, and then the tau 0.5 become tau square, which is 0.25 W square plus 1. And for the angle, normally it become inverse tangent tau W. So there is no tau square over the angle. So we just put inverse tangent 0.5 W for the top, for the transfer function 1 plus 0.5 S. So the third is the time delay, exponent negative 0.1 S. So for this part, the amplitude ratio for any time delay is 1. It's automatically become 1, although you have different value of time delay. Why? Because normally when we take a look on the exponent, the coefficient before the exponent automatically become 1. 1 exponent negative 0.1 S. So we just take 1 here as our amplitude ratio. And of course, for the phase angle, the transformation will be negative theta W. The theta should be referring to the time delay, or sometimes we call it transportation lag. So here, the default is negative 0.1 W. So that means if you have the exponent negative theta S, the amplitude ratio automatically become 1. The phase angle negative theta W. So that is the standard form. You just need to switch or to convert whatever the value you have for the time delay. So for this part, the time delay is 0.1. So you put negative 0.1 W. So this is the amplitude ratio and phase angle for numerator. For denominator, you can see all of your transfer function has the following form, tau S plus 1. Only the difference is in terms of your time constant. Where the first one, S plus 1, the tau is 1. Second one, 0.1 S plus 1, the tau is 0.1. And lastly, 2S plus 1, so the tau will be 2. So this, if we use the standard form, it becomes S plus 1 become W square plus 1. 0.1 S plus 1 becomes square root 0.01 W square plus 1. And lastly, 2S plus 1 become 4W square plus 1 square root. So you can see the form is similar, only is the different depending on your time constant. Similarly, it goes to your inverse tangent. The form of inverse tangent is the same, only the difference is depending on the tau. That's why here you have inverse tangent W, inverse tangent 0.1 W, inverse tangent 2 W. So for this part, you can see there is no sign for the inverse tangent, either positive or negative. That one we will delete later. So in this case, we already convert all of the transfer function into amplitude ratio and the angle. The next step concerns with the combination of amplitude ratio and the phase angle. For the amplitude ratio, we just multiply all of the amplitude ratio we have. So here you can see you have 10 square root negative to 0.25 W square plus 1 and then 1. And then the bottom of your equation, W square plus 1, 0.01 W square plus 1, and square root 4 W square plus 1. So this means this one, you don't need to do the further expansion. You just leave as it is, like this. So this is what we call the expression for amplitude ratio. So meaning that in order to obtain the value of AR, we will convert or switch the value of frequency. So whatever the value of the frequency will determine the value of your amplitude ratio. And then for phase angle, you can see that initially you have 0. 0 is coming from the transfer function of 10. And then you have plus inverse tangent 0.5 W. And then here negative 0.1 W because the time delay automatically become negative. So you cannot change the sign. But you can see in this case, the inverse tangent is positive. Why is positive? Because it is located on the top of your equation. It is located on the numerator. So the definition of phase angle is summation of the angle at the top minus the summation of the angle at the bottom. Or in simple word, angle at numerator minus the angle in the denominator. So that's why for this part, you can see the bottom part, tangent W, tangent 0.1 W, tangent 2 W. You have negative because it is located at the bottom part of your equation or in the denominator. So for this part, when we try to rearrange the angle, it becomes inverse tangent 0.5 W minus 0.1 W minus inverse tangent W minus inverse tangent 0.1 W and minus inverse tangent 2 W. So this represents the expression for amplitude ratio and the angle. So I open to any question that you may have.
Doctor,
Yeah.
so for the denominator dia always plus one dia tak ada akan maybe jadi plus 2, so nanti kena tukar jadi plus 2 juga.
Okay, thank you. Very good question. So let's say in this case, let me create new slide. So let's say in this case, we know that if you have tau s plus 1, the expression, the transfer function, then the AR, by default, it will be square root tau square W square plus 1. And then the angle is the inverse tangent tau W. So this is the standard form. Let's say in some cases, you have GS equal to 2 over 5S plus 4. So in this case, what you should do? So here you can see if we try to break it up, we know that the 2 here, no problem. You have the ability to transform into the amplitude ratio and the angle. But the problem here is 5S plus 4. The 5S plus 4, if we try to compare with the tau S plus 1, is different. In some cases, most of the students, they try to balance it. Okay, for example, here you have plus 4. So they try to convert into the amplitude ratio, it becomes like this. 5, so it becomes 25, W square, and then plus 1, it becomes plus 4. So this is actually wrong because there is no plus 4. The default is plus 1. So for this part, if you have plus other than 1, let's say in this case 5s plus 4, you need to convert it into plus 1. So the equation in this case, you take it out the 4, 5 over 4, s plus 1. So this is the correct way. So this means if you take a look when you try to convert the tau s plus 1, you have different gain in the end. So the gain here 0.5 over 5 over 4 is 1.25 s plus 1. So this is the correct way. So that means if you encounter with the tau s not plus 1, let's say tau s plus 2 plus 3, you need to convert it to become tau s plus 1. So once you have the plus 1 like this, then you can use the default transformation of amplitude ratio and the phase angle. So this is the way. So for this part, it will be good. The good practice is to ensure, for example, the equation you have +1. You have +1 over here, you have +1 over here, you have +1, +1. So when you get +1 over this expression, then you can proceed. If it's not +1, you make sure it becomes +1 before you do the conversion of amplitude ratio and the angle. So that is the good practice. Any further question? Okay, if there is no further question, then I proceed. So in this case, we already obtained the expression for amplitude ratio and the phase angle. So what we want to do next is to plot the Bode diagram. So I believe I already shared with you the standard form of the Bode diagram in the WhatsApp group. So here the Bode diagram consists of the two items, which is called amplitude ratio and the phase angle, where the unit of the angle is degree. So both graph represent what we call it Bode. B-O-D-E, Bode diagram, or sometimes we call it Bode plot. So the Bode diagram should consist of these two items, amplitude ratio and the phase angle. So the amplitude ratio and the phase angle represent the y-axis. The y-axis, and the x-axis here is what we call it frequency, which is referring to your W. So you can see the frequency for the amplitude ratio and the phase angle is tally. It's the same one. So this means we will try to plot based on the given frequency. So since this is the standard Bode diagram and the starting frequency is 0.01, and then it becomes 0.01, 0.1, 1, 10, 100, 1000. So this increment is based on the logarithm. It's log number. So it's different compared to the traditional graph where you have the standard increment, let's say from 1, 2, 3, 4, 5, or maybe this increment, standard increment of 2, 2, 4, 6, 8. So this one is based on the logarithm base 10. So this means in this case, different frequency will be applied. Either you have a slow frequency or faster frequency. That's why the number need to be varied like this. So here we want to plot the Bode diagram. So that means we need to calculate the value of amplitude ratio and the phase angle at different value of your frequency. So the frequency that we are going to use from 0.01 to 1000. So this is the sample of the calculation where you can see in the table here, we have the frequency W starting from the 0.001, 0.01, 0.1, 1, 10, 100, and 1000. So based on the amplitude ratio, you can see this is your W. So this W will be substituted with the respective frequency to obtain the final value of your amplitude ratio. For example, in this case, when I put W equal to 1, the AR is 3.5180. Then we switch to another value of frequency from 0.01, it produce 10, 0.01, 9.9976, and so on. So that means you need to complete this kind of table for the purpose of plotting. Only in this case, I would like to emphasize the angle here, you have the inverse tangent. So make sure in your calculator, your calculator, the mode used should be radian. When you try to calculate the phase angle, make sure the mode used is radian. It's not the digit. Make sure it's radian. So the problem here, when we try to calculate the radian, we cannot do the plotting because the plotting, you can see the phase angle is in degree, where it starts from 90 degree, 45 degree, 0 degree, and then you have a negative value. So this means you need to do the conversion. So once you calculate the value, so here when you use the phase angle expression, it's by default in the radian. Radian units. So once you calculate the radian unit, then you need to convert into degree. So this one, normally you can multiply with the pi over 180 degree. So this is the way to convert radian into degree. You just, whatever the value radian you have, you multiply with the pi over 180 or 180 over pi. So in this case, we have the value of your degree from the radian, where, for example, negative 0.0027, when we try to convert into degree, it becomes negative 0.1546. So in this case, to calculate the amplitude ratio and the angle, both radian and degree. So all information need to be there. The method of calculation, either you use Excel or the calculator, is up to you. But in the end, for the final exam, this table needs to be available for the purpose of plotting. Any question?
Doctor,
Yeah.
if final exam we plotting by Excel, so you accepted juga lah.
Yes, it will be accepted. However,
Oh.
because you need to submit in the PDF file, so you just screenshot. You use snipping tool of this table to the table with the value, and then put it together with the other answer.
Ada Doctor, thank you.
So I think by using the computer, you at least, or the Excel, at least this one can be done faster compared to the manual calculator. So this one is up to you. Both are acceptable. The only unacceptable thing is, let's say you copy from your friends. That one is not acceptable. And then for this case, I would like to remind, normally for this part, you just stick with the 4 decimal point. 4 decimal point. Make sure it's standard. So the common practice is to use up to 4 decimal point. Of course, the minimum decimal point is 2. 2 decimal point up to the 4 decimal point. So that is the standard practice. So here we already calculate the amplitude ratio and the angle for every frequency. So the next step is to do the plotting. So here we have the plotting. So this one is the plotting for the amplitude ratio. So we plot one by one. So let's say, for example, this is based on the table. This is the point. And this is the point. So here, once you locate the point in the graph, Again, this one you can do it in two ways. If you have the smart laptop, you can do the plotting directly like what I did here. You can do the plotting like what I did now. Or if you want to be safe, you can do it in the manual way. You have the hard copy of your border diagram, then you just do the plotting. Both are acceptable. Just to remind you, for the final examination, we don't provide the hard copy. So you need, that means for the final exam of PCD, you need to print the border diagram before the final exam. So this means during the final exam, you already have the hard copy of the border diagram. At least print or photostat 2 or 3 copies just for safety. So the same goes with the face angle. You just do the plotting like this. For example, this is just the example. So in this case, we already do the plotting. There are two things that you need to aware. What we can extract from the phase angle and the amplitude ratio. Okay, for this part, let's take a look on the notes. Okay, if you can refer to the notes uploaded yesterday. So now we use this one, the GP, the GV, the GC, the GM. Now we want to examine the border stability criterion and the gain phase margin. So this is the requirement for the border stability criterion. In order to make sure the process is stable, we need to follow the following requirement, where the AR, OL here stands for the open loop. And then you have the WCO. WCO here represent the critical frequency. Critical frequency. And then here the AR state WC occur at negative 180. Angle negative 180 or negative pi. So the pi here, this is pi value in radian. 180 in degree. If you have the amplitude ratio greater than 1, then your system will be stable. So AR must be greater than 1. Then your system will be stable. So this means we need to find what is our WC first. WC occur at negative 180. So the WC we put at the AR equation and find the value of your AR. If it is more than 1, then we can say if your process is stable. And then the second requirement is the phase and gain margin. So here, to check either our process is stable or not, we use what we call it gain margin and the phase margin. So here the gain margin use the ARC, the same like the border stability criterion, where WC, the critical frequency, occur at negative 180. So we found the WC at negative 180, and then based on that we can determine the ARC. ARC means AR happen at WC. ARC here, AR at WC. So the gain margin can be calculated from GM equal to 1 over ARC. According to the criteria, if you have GM greater than 1, then that means your process is stable. So let's take a look on how it can be obtained. So we know that the GM equal to 1 over ARC. 1 over ARC. ARC occur at WC. WC occur at negative 180 degree. So this is the concept. So we find the negative 180. So this is your negative 180. So this is the point. So here I use different color. So you draw the straight line until it reach your angle plot. So this is your plot. So here you take a look on what is your WC. So according to this, of my example, the WC equal to 8. So this is the value of my WC at angle negative 180. So from this one, we want to find ARC. So how to find the ARC? We need to use the top graph. The bottom graph is for the phase angle. The top graph is for the amplitude ratio. So meaning that you need to draw the next, you draw upwards until you reach the next line. So the next line represent the amplitude ratio line. So from here, you take a look on what is the value of your ARC. So this is ARC, for example, in my case is 0.28. So I have the value of the ARC 0.28. Then I put inside my equation GM equal to A over ARC. So here the GM 1 over ARC, ARC is 0.28 equivalent to the 3.57. So that is how you can obtain the gain margin. So the gain margin here 3.57. So according to the criteria, GM greater than 1, it is stable. So for your case, GM greater than 1. So it is stable. Again, I repeat, in this case, you have the border diagram. The border diagram has two plots, the amplitude ratio and the phase angle. In order to ensure, to determine the stability of your process according to the frequency response, we use the gain margin. The gain margin formula is GM equal to 1 over ARC. ARC means amplitude ratio occur at WC. The C represent the critical frequency. How to determine the critical frequency? The critical frequency occur at angle negative 180. So this is fixed, standard. It's not going to change. So you have negative 80, then you plot the line from negative 180 until it reach the phase angle line. Then you take a look on what is the value of your frequency. This frequency known as WC. For example, in my case, based on this example, WC equal to 8. So here we want to find what is our ARC. So you draw the line upwards until it reach the next line, the amplitude ratio line, and then you take a look. What is the value correspond to this intersection? For my example, the ARC indicate 0.28. So I put the value ARC 0.28 inside my gain margin equation, and the gain margin based on this ARC contribute to 3.57. So according to the criteria, when you have GM greater than 1, your system is stable. So this is how you can interpret the stability according to the frequency response. Any questions so far? So in this case, we use not only the gain margin. If we take a look on this slide, we have the gain and phase margin. So normally both need to be applied together. Not only the gain margin, we need to supplement it with the phase margin. So for the phase margin, we use the following criteria, where the WG is called cost over frequency. WG stand for the cost over frequency. The WC stand for the critical frequency. So here you have the WG, where the WG occur at AR equal to 1. So this is by default of the phase margin. And then once we obtain the AR, we will do the plotting again to find what is the angle corresponding to the AR. So here to calculate the phase margin, PM equal to 180 plus the angle. If we have the phase margin greater than 0, then that means your system is stable. So this is another criteria. Before this is gain margin. Now it's based on the phase margin. So we take a look on our graph, how to find the phase margin. So here we know that the phase margin 180 plus your angle of G. I just put G to differentiate with the angle. So the angle G here occur at AR at WG. WG occur at AR G equal to 1. So this is the fix. So meaning that the starting point should be ARG equal to 1. So we draw the line, we start finding the AR equal to 1 starting from here. So this one I use another color. So this. So 1, we draw the straight line until it reach the graph, the amplitude ratio line. Then we find what is our frequency. So for this part, the frequency is 3. WG equal to 3. So in order to find the angle, we go downwards until it reach the next line. The next line corresponds to the phase angle line. So from this one, once you obtain that, take a look on what is the angle. So here, let's say your angle is negative 135. So the phase margin here, 180 plus the angle negative 135. So that means it is what we call it 45 degree. So since the PM greater than 0, then this considered as a stable system. So that's how you can interpret based on the gain margin and the phase margin. For providing the or for obtaining the system, the stable system, both need to be satisfied. The phase margin and the gain margin. If one of the criteria is not met, is not fulfilled, let's say in this case your GM greater than 1, but the phase margin you get negative. So still it is called unstable system. So you need to meet all of both requirements. PM greater than 0, GM greater than 1 for achieving stable system. So for this part, based on the body diagram, just to wrap up, the WC equal to 8 and the WG equal to 3. So we calculate the GM equal to 3.57, the phase margin equal to 45. So this means according to the gain margin and phase margin, your GM greater than 1 and your PM greater than 0. So the system is considered stable because it satisfies the stability requirement. So this is known as the Bode stability criterion. So another criteria that we are interested is the well-designed control. Here, when you refer to the slide, you have the rule of thumb, a well-designed FB control. FB here represent the feedback control, the type of the control that you are going to use. Feedback control system must obey this requirement. 1.7 must GM less than 2. 30 degree PM less than 45. So this is another requirement for well-designed FB control. What is mean by well-designed? So here we will investigate the suitability of our control. Okay or not, our control. So in this case, we use based on the given example, if we take a look, we use PD control. So we want to check our PD control okay or not. How to check? We use the following criteria. The gain margin must be between 1.7 and 2. The phase margin must be between 30 and 45. So according to this, since your GM 3.57, your phase margin 45. 3.57 is in the range. 45 on the border. So here we can say that the performance of the controller is okay, is satisfactory because it's in line with the range, although the phase margin on the border, but still we consider it okay. So this is the two criteria. The gain and phase margin before, when you have greater than 1, greater than 0, is based on the stable system, stability. The guideline for well-tuned controller must follow the following range. In some cases, you may have a stable system, but the controller is not good enough. So it will fall outside the range. So this is the thing that you can determine the effectiveness of your controller and the suitability of your closed loop transfer function. Any question that you may have? So in this case, the gain margin and the phase margin has been obtained from the Bode diagram. So that means based on your plot. There are another method to obtain the gain margin and phase margin without the use of Bode diagram. So this is the second approach, using calculator to determine the phase margin and gain margin. So from here, you can see the GM equal to A over ARC. The GM equivalent with the 1 divided by ARC, where We know that ARC occurs at WC. WC, meanwhile, occurs at negative 180 or negative pi. So what we need to do is to use our expression for phase angle and the amplitude ratio. For this part, we use the phase angle because we know the phase angle must be negative 180 or negative pi. We set negative pi, so that means in this case, we can predict what is the frequency required to achieve negative pi. So from here, you can use the shift soft option in your calculator. I believe because of all of you use the scientific calculator, you have the ability to determine the unknown variable inside your equation. So here, since we have one unknown, the frequency, you have the y, which is negative pi. So you can directly solve the model, the equation. So here, when we set angle at negative pi, it contributes to the WC equal to 8.2455. So from here, you can see the WC is used at the ARC because we want to calculate the ARC. So this W represent the WC. So we put the value inside to determine what is our ARC. So for this part, ARC equivalent to the 0.2385. So once we obtain that, then we get the GM equal to 4.1929. We can see in this case, before this, based on the plot, we get WC equal to 8. Based on the calculator, you get 8.2455. Which one is the most accurate? Of course, using the calculator. Because in the plot, you don't have any decimal point. You just get 8, 9, 10, like that, the round off number. But here is much more accurate by using your calculator. So here we have the gain margin of 4.19. The same goes when we want to calculate the phase margin. We know that the phase margin equal to 180 plus angle at the G. Angle at the G, gain cost over frequency occurs at WG. WG occurs at the AR equal to 1. So we use the amplitude ratio expression, we put equal to 1 to find what is the W here. Similarly, you use the calculator using the shift soft button and then you get the WG equal to 2.75 or 7. Once you obtain this one, we put inside our equation. Now we want to find the angle, so we use the phase angle equation. And we find that when we put 2.7547, we get the angle negative 2.2153. This equivalent to the negative 126.93. And of course, in this case, since you get different angles, you get the different criteria, 53.07 degree. So the value obtained from the calculator and the plot could be different. It depends because in the plot, it will depends on how do you calculate the value and how do you plot the graph. So the value tends to be different, but both are acceptable for calculation. In this case, how to know either using the plot or not? Normally in the exam, we clearly state if we require the plotting, we ask you to plot the border diagram. So that means you don't have any choice to do the plotting. If the question does not mention anything about the plotting, then you can choose either using the plot or the calculator. Let's say the question asks you to determine the stability of closed loop transfer function based on the frequency response. If that is the case, then you are free to use either using calculator or plotting. Both are acceptable. So this is the thing that we can obtain from the frequency response. where here I emphasize two methods, either using the plot or using the calculator. So I let all of you digest the information first. We take a break and afterwards we continue with another tutorial. So we take a break now for 5 minutes.
Alright, Doctor.
Ahmad Akif ada tak? Mana Ahmad Akif? Ahmad Akif.
Akif.
Aha.
Macam
Tak ada nama dia. Mana dia pergi dah?
tak tahu dia cak, saya cuba call dia doktor.
Tak apa, WhatsApp je dia.
Boleh.
Terima kasih.
Sama doktor.
All right, let's continue for the last part of our class. So in this case, we refer to the tutorial. So in this tutorial, I provide two types of question. So the first part here, if we take a look, the question relate with the block diagram, where we provide you the control. We give you the parameter of the control, where the Kc equal to 10 and tau d equal to 0.5. And the type controller that we are going to use is the proportional derivative. In some cases, there may be the controller is not provided, or they just give you the type of the controller that will be used without the controller parameter. So this is another type of the question that I would like you to consider. So let's say we take a look on the second question. For this part, the block diagram of conventional feedback control system contain the following transfer function. So in this case, you may notice that the transfer function will be given to you. So you don't need to worry about the transfer function. So what you need to do to employ, to use, to apply the transfer function into the frequency response aspect. So here you have the GP, you have the GV, KIP, KM bar, GM, and DD. Oh, there are 6 block diagram, 6 transfer function given to you for this part. So do we need to use all? All right, we take a look on the question. A, here if the proportional integral control is proposed, determine the value of ultimate gain. So in this case, they just propose the controller, but they didn't give you the value of PI. So if they didn't give the value, you need to calculate it. So you cannot assume it. So here the question A relate to calculate the value of PI controller using Ziegler-Nichols method, and then the B is the same thing. Once you obtain that, you can calculate the phase margin and gain margin based on the plot. And then C, evaluation in terms of the gain margin and phase margin. Do you reach the stable system or not? And how your controller performance based on the guideline of the well-tuned controller. So C is determined based on the outcome of your B. So for this part, the PI controller is not given. So we know that PI controller has the following form. So this is our PI controller. So where the PI controller here, you have two parameters, Kc and tau I. The value itself is not given. So if we take a look back to the question again, here you have 1, 2, 3, 4, 5, 6, and 7. Meaning that if we try to represent it in the block diagram, it becomes like this. We know that the block diagram, you have this, and then you have the Km bar. Then you have this, you have the GC, and then you have the GV. You have the GIP here. You have the GV. You have the GP. Then you have the GD coming to this. Then you have the GM. So this case, you have this block diagram. So you have the KM bar, GC, GIP, GV, GP, GM. So you have 1, 2, 3, 4, 5, 6, 7. So you have 7 transfer function. But for frequency response, you need to understand, we just use the transfer function which is available in the loop. TF stands for transfer function in the loop. So for this part, the loop is here. This is the loop. So this is your loop. So this means the KM here, the GD here is outside the loop. So you don't need to use this information because it's not part of the loop. It's part of the block diagram, but not part of the loop. So meaning that here we need to use the GM, GC, GIP, GV, and GP. Where the GIP, you have the information of the KIP. GV, you have the transfer function. GP, you have the transfer function. GM, you also have it. The problem is your GC. GC, in this case, they just give you the type of controller, the PI, where the PI is 1 over 1 plus tau I S. No parameter. So that means we need to find the parameter first. So since you don't have the Kc and tau I, you cannot assume the value Kc equal to 1, tau I equal to 1. That one is clearly wrong. So here the question asks you to calculate the controller parameter. So in order to calculate it, we know that the G inside the loop should be like this. GP, GV, GM, GC, GIP. You have 5. The problem here, GC is unknown. Unknown because you don't know the parameter. Unknown. So we exclude the GC first. We just use the GP, GV, GM, GIP. That's why in this case, you can find this is the equation. GP equal to GV, GM, GP, and GIP. So here the objective is to find the ultimate gain, KCU. So here if we take a look on the slide, KCU referring to the maximum value of Kc that result in stable closed system, where the KCU equal to 1 over ARC and the ultimate period PU 2 pi over WC. And this is the formula for calculating the controller parameter. There are two formulas that can be used. The first one is what we call it Ziegler-Nickell. Ziegler-Nickell, where you can calculate the P controller, PI controller, PID controller. And the second one is called Tyrus and Lieben, where this one is only applicable for PI and PID. So the question asks you to calculate the controller parameter using Ziegler-Nickell. So we are going to use the following formula. So in order to obtain the parameter of the Kc, tau I, because here if you recall, we know that for the PI control, the GC equal to Kc, 1 plus 1 over tau I S. Here the Kc, tau I is unknown. So for this part, based on the Ziegler-Nickell, we know that Kc equal to 0.5 KCU. So this is the formula using Ziegler-Nickell. And the tau I can be calculated using PU over 1.2. This one. So once, in order to obtain the Kc and tau I, that means you require the value of KCU and PU. So KCU can be obtained from this formula. KCU equal to 1 over ARC. PU can be obtained from this formula. PU equal to 2 pi over WCO. So we are going to use this formula to obtain the controller parameter. So in this case, we know that KCU equal to 1 over ARC. 1 over ARC. So what is the ARC? ARC, we know that AR at critical frequency, occur at WC, occur at angle negative 180. So that's why here we use this one. AR, so this one ARC occur at WC where the phase angle negative 180 equal to negative pi. So now we don't have the amplitude ratio expression. So we are going to develop it. So here we don't include the GC because we want to find the GC. So we exclude it first. So that's why you have the GP, GV, GM, GIP. So based on this is the following transfer function. 19.5 over S, 1.21 S plus 1, 0.2 S plus 1. So from this, we classify term by term and convert into expression of amplitude ratio and the phase angle. So here, based on this, we can find that the AR equal to 19.5 divided by W square root 1.4641 W square plus 1 multiply with the 0.04 W square plus 1. And the angle equal to negative pi over 2 minus inverse tangent 1.21 W minus inverse tangent 0.2 W. So this is the expression based on the G equal to GP, GV, GM, GIP. So we know that AR occur at WC. WC occur at negative pi. So we put negative pi over here on the phase angle to find what is our WC. By using calculator, we found that the WC equal to 2.032. So once you get the WC, we substitute into the AR equation. We put this WC equal to 2.032. Now, based on this, we can find our ARG at WC, where the ARG here, 3.3494. So, we know that the ultimate gain for the controller KCU equal to 1 ARG WC. Here, this one reflect not ARG multiplied with the WC. This one refer to the ARG at WC, which is 3.3494. So KCU equal to 1 over 3.3494, which contributing to the 0.2986. So this is your value of your KCU. So we know that the KCU value. So we refer to the following table where the Ziegler nickel have the following formula. Kc equal to 0.45 KCU. And then the tau I equal to Pu over 1.2, where the Pu equal to 2 pi over WC. So from the previous procedure, we know that WC equal to 2.032. We insert it back, the value, and then this is the value of your ultimate period. The Pu here, ultimate period. So this ultimate period is 3.09. So this means we can substitute this value inside the tau I. So for this, we already know the KCU and PU value. So we substitute both value to determine the KC and tau I. So for this part, the KC equal to 0.45 KCU. 0.45 multiplied by 0.2986, we get 0.1344. And tau I equal to Pu divided by 1.2. So 3.0921 divided by 1.2, we get 2.5768. So this contribute to the controller parameter, the PI controller. So now, this is our expression for PI controller. So we know the value of the Kc and tau I. So where the Kc is equal to 0.1344 and tau I 2.5768. So that means by using the Ziegler-Nichols method, we can obtain the controller parameter. So no need to do the assumption. So what to do next? Once we have the controller parameter, of course, we just repeat the same step like before. We include the term inside our equation. So you can see here, now we have the GC. Before this, we don't have the GC. Now we have the GC. So we have the GC together with the other transfer function, the P, the V, the M, and the IP. So for this part, we just do the similar step. Since we add one transfer function, then it will change your frequency response. So we obtain another for new form for amplitude ratio and the phase angle expression. So for this part, this is our overall amplitude ratio and overall phase angle. You can see it's a little bit complicated, but it's normal. So, and this one is for the phase angle. So this amplitude ratio and the phase angle represent the GP, the GV, GM, GIP, and your GC. So this one, when we obtain all, then we will perform the border diagram, the gain margin and the phase margin to evaluate either process is stable or not. Before this, no controller. We don't know the value of the controller. We can evaluate the suitability of our controller. Now, since we have the value of the controller parameter, then we can evaluate the stability. So for this part, let's say we do the plotting. We put the value of the frequency and calculate the AR and the angle, both in radian and degree. So for this part, so let's say this is our diagram. Then based on this, we just follow the same step in order to find the gain margin and the phase angle, where the gain margin 1 over ARC. The phase margin 180 plus angle at the G. So for this part, we can say that for the graph itself, you don't have any gain margin. Because here you start at the negative 80 and the line start at the negative 80. So that means there is no gain margin available. But for the phase margin, you can start from 1 until you approach the line, go to the bottom, then you take a look on the angle, which is in this case negative 195. So here the phase margin can be calculated 180 plus negative 195. So you get negative 15. So clearly this one, since you get negative phase margin, automatically become unstable system. Meaning that in this case, the controller itself provide the unstable system and thus should not be used. Although you use the PI controller here, if we try to take a look, since you cannot calculate the AR, let's say ARC is too big and outside the border diagram range, I just assume 1000. When I put 1000, you can see the gain margin is too small, 0.001. And the phase margin here, negative 15. So based on this, we can say that it violate the stability requirement and it become unstable. And if we take a look on the well-tuned controller, of course, it is outside the range. The value that you calculate does not satisfy the range. So this contribute to the conclusion. PI controller used in this case cannot be applied. It provides the unstable system. How to further improve? Use another controller. Let's say for the PID, or you calculate again the controller parameter using different tuning method. So this tutorial provide two ways, two form of the question that will be asked during the final. Either we give you the controller parameter, then you just straight away do the calculation. Or if you don't have the controller parameter, make sure you calculate it first. Once you calculate, then you perform the normal procedure of project diagram to check either your process becomes stable or not, or the controller parameter obey the well-tuned controller guideline or not. So this is the thing that is covered for the frequency response. Normally, this question is the what we call it the question that is preferred by the student because it provides easy mark to score. So normally in the final exam you have 3 questions, and this provide the question number 3. And almost all of students answer this question first because it is the easiest one. So any question regarding this? Okay. So I think this is the end of our class, and this is the last topic to be covered for the process control and dynamic subject. Just to share with you, the final exam question will consist of 3 different questions in one set. One question around 33 marks. So question 1, 33 marks. Question 2, 33 marks. And question 3 is 34 marks. So in total, you will have 100%. And this will be converted into 60%. The first question is like the open loop. The chapter 1 and chapter 2. Chapter 1 and chapter 2 represent the first question. That means you need to do the derivation until you get the transfer function before you can solve the transfer function. Question 2 represent the controller, the closed loop, which means how to obtain the closed loop transfer function based on the set point changes or disturbance changes. Then you calculate the offset. You determine the stability based on the Roos array method. That is the second question. And last question is this, the frequency response, which is based on the chapter 4. So that represent your final exam question soon. Any question relating to the final exam?
Doktor,
Ya,
each question berapa markah tadi, Doktor?
33. 33.
Okay, thank you, Doktor.
33, 33, 34. At least based on 100, we divide by 1/3. Any other question? Okay. I think since there is no question, Ahmad Akif dah ada.
Dah ada Doktor.
Selamat tengah hari Ahmad Akif.
Selamat tengah hari Doktor.
Alright. Okay. Of course, in this case, you have the submission of the PD of the simulation report of the project. So that one to be submitted by end of June. And then, of course, the final exam later on. So that is the remaining assessment for all of you. In the case you require further assistance, you can contact me in the WhatsApp or you can call me for consultation. No problem. So that is the last thing, I think. The topic that will be covered from chapter 1 to chapter 4. So with that, I personally, first of all, I would like to say thank you very much for all of your participation, for your responses, for your interest in this subject. And I wish the best of luck to all of you in the final examination. So with that, thank you very much again. And we end our class for this semester for process control and dynamic. Thank you very much and have a good lunch.
Thank you, Doktor.
Doktor.
Thank you, Doktor.